Okay, I'm just going to check that I can hear myself so we don't have the audio mishap again. Okay, I'm just going to check that I can hear myself so we don't have the audio mishap. Okay. Alrighty. So we are on to tabular data for, oh, I forget I have to introduce myself. So I'm Christina. I am a lead data scientist or a data science manager, I guess now. Um, and I am kind of retraining myself in some basic coding principles so I don't get rusty myself because I still sit kind of between technical and non technical. And this week we will be learning PyTorch again. I did it years ago when it first came out with the Fast AI course, and I'm doing it again, just walking through the notebooks and making sure I understand how it works and caveats and things like that. And next week I'll be working in like C++ and CUDA, trying to get some more um, deep learning skills under my belt so I can use them to train people on and implement some things I find cool. So we are on 9 tabular data, and it's the ninth notebook. It's a combination of chapters in their Practical Deep Learner for Coders book by Fast AI. I like their book because they give lots of examples, and they also integrate their API, which is a very nifty API to use. And so we're going to be going through this today. Thanks for joining if you're tuning in and following along. And I believe we started a 28-day journey, and we should be on day 20, counting down. So we're on day 5. So we have 23 days left of me showing up and getting this done and holding myself accountable to stream the learning. So, tabular modeling. Yesterday we did a look at collaborative filtering or recommendation engines, and then how you could do that in PyTorch, and what are some of the caveats and trade offs of how these systems are set up. And today we're going to be looking through tabular modeling, I think NLP, and we might get to mid-level data today as well. We're going to start here and go from there. All right, so tabular data is a spreadsheet or a CSV. Um, and yeah, the most common, more general techniques used are random forests. And honestly, I dump a lot of stuff in random forest as tabular because it's just really quick and easy to get stuff out of. With boosting trees, they run better on GPUs oftentimes. So I typically, depending on what type of client I'm working at, don't get to use it because they don't have GPU access and it takes forever. Like you can use CPUs and you distribute it across it, but I don't always want to. But a random forest doesn't need that. And for a lot of business use cases, the simple answer sometimes works. All right, for our categorical embeddings, what we'll be talking about is determining different categories like age and sex, and then they have numerical data, which feeds directly into the model, but the other columns, like converting them into like categories. So you might make age into a category of like 25 and under, 50 and above. Um, so they're talking about a Kaggle competition where we had various stores in Germany tasked with predicting sales. Entity embeddings paper we can read. Entity embedding reduces memory usage and speeds up neural networks compared with one-hot encoding. But more importantly, by mapping similar values close to each other in the embedding space, it reveals the intrinsic principles of categorical variables. It's especially useful for data sets with lots of high cardinality features where other methods tend to overfit. As entity embeddings define a distance measure for categorical variables, it can be used for visualizing categorical data for data clustering. Uh, An embedding layer is exactly equivalent to this placing an ordinary linear layer after one hot encoding layer input, and they have a diagram to show it. That's not loading. Actually, that's been happening a lot. So let me pull up their GitHub. So there we go. Um, so a dense layer is the same as a linear layer. And so we start with an output dense layer 1. So these are two linear layers. We have EE layer and one hot encoding layer. Okay, so it's an embedding layer. Embedding layer, one hot encoding layer. So yeah, the first thing we did was train linear layers. All right, so let's look at this. This is a embeddings based on a map. This is the embedded matrix for possible state category, or category we can call possible values of a variable. Its layers or categories or classes. So one level is Berlin, the other is Hamburg. On the right is a map of Germany. The actual physical locations are slightly different and were not a part of the value physically weren't there, but just the model of the state was. Behavior of store cells. Okay. So remember how we talked about the distance between embeddings? The authors of the paper plotted the distances between the store embeddings against the actual geographical distance, and they found they matched very closely. So yeah, that's a bit closer. So distance in the embedding space. So how far apart they were here and how far apart they were on the graph is mimicked here. So if they plotted the embeddings for days of the week and months of the year, they found that the days and months that are near each other on the calendar ended up close in the embeddings too. So these are Monday, Tuesday, Friday. Things drop and go back up on Sunday. I guess it's their prime times. And then the same for behaviors of sales. It goes up in March, goes up in October, November, and takes a dumpster dive in the summer months of December and where they sit. So fascinating that they stay in order. This stands out in these two examples is that we provide the model fundamentally categorical data about discrete entities, and the model learns the embeddings for these entities that defines continuous notion as distance between them. So they found the distances between them, like the order they're in, even though it wasn't told. Fascinating. Learned based on regular patterns in the data tends to match up with our tuitions. So in addition, it is valuable, it is all right that the embeddings are continuous. This model are better at understanding continuous variables. This is unsurprisingly considering the models are built of many continuous parameter weights and continuous activation values, which updated the gradient descent, a learning algorithm. Yeah. Another benefit is that we combine our continuous embedding values with truly continuous input data in a straightforward manner. We just concatenate the variables and feed the concatenation into our first dense layer. In other words, the raw categorical data is transformed by an embedding layer before it interacts with the raw continuous data. This is how FastAI and Gao and Burkhan handle tabular models containing the data. So let me read that again. The raw categorical data is transformed by the embedding layer before it interacts with the continuous input data. So this is the raw embedder that is transformed before it interacts with this one, I'm guessing. Right? Or is there being the one hot encoding ladder? Okay, so an example using this concatenator was just Google does its recommendations on Google Play. Cool. So Google is just using, well, it's not surprising that they're using deep learning for it, but how does it work? We have their categorical features, such as this, and they create embeddings of their categorical features, and then they concatenate them together, and then they, what is that, negative values to continuous values, right? I keep forgetting what it is. I will remember it. Do that 3 times. Take the log laws and then cross product transformation. Okay, the cross products, they took the dot product here. Most machine learning courses will tell dozens of different. I completely agree with previous technology confused about which techniques works where. So can conceal down. So ensemble of decision trees, which I like. Boosting a random forest, mainly for structured data. And that's typically what I deal with. Multi-layered neural networks with stochastic gradient descent, which is shallow deep learning, which I use for mainly unstructured data. 2 categories you should know. And you'll typically, I would say, probably only work with one or the other in your career. Some people, because there's like specialties, right? And so you don't always get to work across multiple. So being really good at one or two within the category you're used to and expanding in your career would be great. So deep learning is nearly always clearly superior for unstructured data. These 2 approaches tend to give quite similar results for many kinds of structured data, but ensembles of decision trees tend to train faster, are often easier to interpret, and do not require special GPU hardware for inference at scale, often require less hyperparameter tuning. Um, they have also been popular for quite a lot longer than deep learning, so there is more mature ecosystem of tooling and documentation around them. Yep. Most importantly, when interpreting the tabular data is significantly easier for decision trees. I agree. Which columns are important, which are related to the dependent variable interactions. Yeah. Our first approach, yeah, decision trees. Love those. Skyline is when the data set meets one of the conditions. There's hardly cardinality values, like a lot of discrete level represented in them. Something like a zip code, which has thousands of possible levels. Yeah. And columns that contain data that's best understood within neural networks, such as plain text data. Um, in practice, when we deal with data sets that meet these exceptional conditions, we always try both decision tree ensembles and deep learning to see which works best. It's likely that deep learning will be a useful approach in our example of collaborative filtering, as we have at least 2 high cardinality categorical variables, the users and the movies. But in practice, things tend to be less cut and dry, right? And there are often a mixture of high and low cardinality, categorical variables, and continuous variables. Either way, it's clear we're going to add this industry. Okay, got it. So let's look here. Um, let's skip that part. So we're going to look at Blue Book for Blue Dozer's Kegel competition, which is to predict the sales price of a particular piece of heavy equipment at auction based on its usage, equipment type, and configuration. It is sourced from an auction results page and includes information on the uses of the equipment configurations. So, yes, I know what Kaggle is. And if you don't, it's a competition website, and you can use it, but and compete for stuff and sort of so forth. So they're using that, and they don't want to download it here, so you can just import it and then download it instead of just moving the CSVs. That's all they did here. So we look at the data. We have these four fields. I don't know what I'm looking at. They're column names. The brain is just like, what is it? These are columns. These are what we have. And it is 100% always good to look at the data to know what on earth you're working with, because in context, what you're looking at might not be what you're looking at, and you think you know, but you never ask the question. That has happened to so many people. They assume something that wasn't true, and it doesn't help get you there. Even if you need to read a description of the data, the actual data may not be what you expect. Exactly. It's a good idea. Low memory false. Yeah, it's pandas. Okay, so these are all of the columns available. Wait, what was this then? Oh, they provide information about it, so it tells you what it is. But this is all the columns completely available. And trying to make sure you understand, like, this is large, medium. Well, that's screwy, right? You have a large, you have a medium. Why is this large, medium? I hate it when that happens. But that's sucks. Um, um, that sucks a lot. And so they turned it into a category, and this will turn it into a set of codes so that you don't have to worry about this stupidity. Like, who did that? Why is there an in-between size? Why couldn't you just come up with another name? Why wouldn't... Never mind. I hate it when that happens. I've seen a lot worse than this. I'm sorry, just, memories of how did this decision get made. But yeah, so that doesn't matter. You turn it into numbers, right? And it might matter when you analyze and present your report, but for you to just get started, turn it into a number. And so that's what it does, right? Now, we need to, the most important data column is a dependent variable. It's one we want to predict, right? And so we kind of really need to know what that is going to be. Oftentimes in Kaggle, it's going to tell you what metric you're going to use to confirm your predictions, and they're going to, for this case, they're going to use root mean squared log error, right? To check that the actual and the error rate between the actual and the predicted values, right? And so we're going to process, right? And so we're going to take sales value, price, and that is going to be what we predict on, okay? So they just plug this in here because they don't have to. One of the reasons you do it this way is so that everywhere you use it, if this ever changes, you only update it in one place. You don't have to update it in every instance of your code. That is so important. I used to do this all the time when I was a junior. And I had to make so many code updates, but there really is something to setting your parameters all at the top of the file and only having to update that one column once you finalize your model. Yeah, it saves so much time. So here they take the log of this, and that's how you're going to get the log there. Okay, so let's look at this decision tree. One of the heavy benefits of decision trees for tabular data is quite simply, it's going to try to tell you how it got to that point, that decision. And that's going to be good for you because oftentimes people are going to have questions. How did it get this way? Why did it get this way? I just thought of something. Hold on, I need to message a team member. I hate when that happens. Like, I'm thinking of one thing and I think of something else. So here they are going to kind of create yes and no statements. That's what a decision tree is, right? Is this true? Is this not true? And so this is like, are you less than 30? We're not answering this question about myself. But either way, you either choose eat healthy or exercise, right? And you can either have yes or no on either of these. And that's kind of how it does. And it'll go through all of those. Um, every decision for every decision for one of the row, like the predictions, not rows, predictions, it'll make this tree. And so you can pull out this tree and you can look at it. And as you get into more decisioning, it really does help because you get into more complex machine learning, and looking at those trees can help you make better informed model decisions just depending on what you're working on. So we, in order to do that, have the basic steps of training a decision tree model. And that's really simple. Load it, look through it, um, split it off, and then, predict the average. Find the average of each. Um, Actually, I've never written out the steps of decision tree model before. I presume this is good practice, though. I've never written it out. I just understand how they work. But loop to them, pick a splitting point, split into more groups, and continue doing that. Basically, yes or no, split into groups, yes or no, split into groups, yes or no, split into groups, until we get to the end, right? Um, and one of the things um, it's going to split so many times. Like, how will it choose the correct one? It chooses the greedy approach, right? And also, by the end of it, if you're doing a random forest, right, it's just averaging all of it together to get its final prediction. So it's taking a bunch of full trees and averaging it together and getting a final prediction so that you know better. Um, so that you know better about what you're looking at. Boosting trees do partial runs, whereas random forests do full runs, but they just average it together to make the best prediction. And that is really nice. It's like a voting system. I guess is the best way to explain it. Actually, I think I wrote a whole ebook on this because I was going to use it to get people to sign up for my newsletter. And if you haven't, please go and do that. Um, I really would appreciate it. I have a few different ones coming out. My daily one, which is kind of very thought provoking and a little sarcastic. And I'm working on one around teaching the basics of statistics every day. So look forward to that. Anyway, handling dates. Um, oh, my brain just went down like a whole rabbit hole. There's a lot of stuff I want to know what they are going to do. So dates are definitely ordinal. So they pick, yeah, this is built in by them. I used to love using that. I forgot about it. They get the data frame that you tell them the date, and they pick it out right. And they basically splits off into all of these parts for you. That speeds up so much that you don't have to do that yourself. Now, I'm guessing this has, these are some useful wrappers for pandas. And I think the only downside to using this is if you're using a lot of data and you want to use the fast AI, I don't think they have wrappers for like Dask or Polars, or there's like another one I keep forgetting. There's one up and coming. I think Mojo is up and coming. But they don't really provide wrappers for it. And it's a small development community, probably a good open source project to get involved in, especially since the field is going toward a lot of engineering right now. And what they need, they don't really want more statisticians. They want people who can engineer these things. So getting more hands-on development experience for packages, even just in Python packages, would be really good. So category 5 replaces a column with a numerical category column. And this replaces missing with the median of the column and creates a Boolean column that is set to true if the value was missing. So you could have both. So useful. Oh, I like them so much. They think of all the things. Okay, so Tabular Pandas also handles splitting the data set into training and validation. However, be careful about that. So you can have a training and test set. You can have a training, test, and validation set. It really just depends. The validation set validates the training model, and the test set you don't even get to look at. And it really just depends. Since this is a date range, typically I would not take a random subset, and I don't think they take one either. Since it covers 6 months of data, I'm pretty sure they take narrow it to like data from before November 11 and everything after would be it. You want to make sure it's ordered. I've seen this mistake happen. Like you get time series data and you don't know that you should order that thing. Order it so that you're predicting for the future because that matters where its placement is in time. And in business data that is across time that you're looking at really does change based on user buying behavior, business promotions, business strategy. All of that changes and it's reflected in the data. And that's why you often have drift in your data. And so making sure your set is trained on order and on an order time series is important. So this is them just checking that that is true, that they are training on the right time data. And that they're splitting with the right amount. And so the training data set is a lot larger than the validation set. And this is how it looks. And oh, I should probably be narrating what I'm looking at. I got distracted. It was fun. Okay, so it's showing 3 of the outputs, right, for the split. And that is Tabular Pandas right here. So it's showing 3, right? And then it's showing the input that's going in, and it's showing the reduction items that are numeric, right? It's just reading out all of that and other items. And they showed how they replaced it to numbers and saving it to a pickle. I'm going to say this again. I said it, I think, a few days ago. You do not need to reprocess your stuff every single time you come to run your code. Save it, whether it's your model or your pre-processed data, save it and don't waste that computational time. It's one of the biggest loss killers of your time at work and the time you're doing to develop. Save it. Okay. I'm off that rant. I probably will have to give that rant a few more times over this year to someone on the team, like just save it. But a lot of people don't know you can save. I didn't know when I first started out that I could save. No one taught me. But it is something you learn and you use regularly. Okay. So if we define our independent and dependent variables, it results a pickle, and we set up a basic decision tree regressor, right? It's going to have 4 nodes, very simple, not even a random forest, but it's a regression model. And they are using scikit-learn. And this is what comes out. So this mean squared error is 0.48. This is the number of samples that went in, and this is the value. And this is how many samples went to the false, and this is how many samples went to the true. A lot more went to the true. And then it looks at this one, and it goes to true or false, and it just keeps breaking down. So yeah, this would be the initial model, as they call it, and it splits. Yeah, and that was the error, right? Said that. Trying to make sure I didn't miss anything. Coupler system. Okay, yeah. Coupler system. And this isn't displaying, so this is less than. So that's what it's saying. Coupler system less than 0.5. Your made is, we don't know what that is because it's not displaying properly, but something about 1995.5, so like June. Product size, something about 4.5. That's just the criteria it was split on. Um, and this value, like the average value that it gave when it did these splits, right? Oh, that's right. And since there's no more criterion, there are no more questions it can ask because this one only had these, only had 4 columns. Where is it? Yeah, it only had the 4 columns, the coupler system and the whatever. I think, is that what we're saying? That they only took in a certain amount to ask questions on? Okay. Okay. I've never seen this module before in my life. This is so cool. We're saving it. Okay. I don't have, I have a bookmarker. I'm going to copy this to my bookmarker. Can't believe I missed this my first time through. What was I doing? I think it was right before COVID. My brain was not on. This is where my bookmarker is. My brain was not present. There we go. Tool saved for the future. You should definitely have a way to save stuff that you find online because you never know when it's useful. I even save like LinkedIn posts because it mentions something that I know I'll need later. And then I bookmark the post for the person who brings up the topic on like a package or a technique or something. LinkedIn is more for just socializing. Okay, so this is the data tree fizz, and this is really cool. So we graph the coupler system metrics with the sell price prediction, and then the sell price here, and then the here made. A lot of it's more skewed this direction, right, than that direction. Uh, Sales price was here, here, here at the end, of the product size we split off between the 4.5 and the 6, right? And so this does random permutation length. So they took, I guess, a random sample of 500 and to sample index, yeah. And here they chose, a font, left to right orientation, or maybe I did learn this before. And the columns, the dependent variable that we saved, and the sample indexes, right? And so this is a distribution of data for each split point. We can clearly see there's a problem with our year made data, right? It's all skewed here and here. And that normally means, I'm not gonna say what it normally means, but it does normally mean if it's a strange date, that is a placeholder. It's a placeholder date that just means missing, or it might actually represent a certain product from a certain provider that doesn't have the year. You have to ask people. It might not even mean it's missing. It could actually mean something for a specific product, and that's just they don't have the year. And so it's technically missing, but it represents a product, so it's actually a skewed point. Presumably, it's just a missing value code. For modeling purposes, it's fine, but you can find outlier makes visualizations are more difficult. So they change it to a different, closer value so that it doesn't skew to 1950 so that it visualizes better. And so now, because none of the data must have had a 1950, right? And so now we have, because 1950 is here now. Well, duh, because it's 1991. Sorry, I am having a long day, as usual. So between here and here, what are we looking at? So it gives a much better graph. And so Uh, RMS. Check the root mean squared error. Oh, yeah, mean squared error and root mean squared error. Okay. So to do that, you take the mean squared error that you found, and you just get the mean root of it, the mean of it. Yeah. Well, I guess they just do the whole calculation again to get the root mean squared error because they take the square root of it. And then they do the predicts on it. And they check the validation set. And it doesn't like it. There's a lot of overfitting happening. And let's see why they say it is. So it created a lot of leaf nodes as data points because the other one's built on, I guess, a larger data point maybe. So get leaves. So it has leaves and leaf nodes. I'm not sure which one is which. I can pull up the documentation and it will tell me which one is which. Leaf and leaf nodes. So scikit-learn decision tree regressor. Okay. Let's look at the output of get in leaves. It just returns a integer. I'm reading something wrong. Let me see if I'm reading my code wrong. Oh, I am reading my code wrong. Silly. So this is the number of leaves because this is the comma. This is the number of leaves, and this is the number, of data points. See, slow moments in front of my face. And I'm hunting down documentation because I didn't read my face. My mind was not reading the full code line. Okay, so yeah, that is very over enthusiastic for a model. So we kind of need to change some of the default settings, right? And so they changed the minimum sample size, and I do this all the time as well to make sure it didn't do that. So now it's going to calculate the root mean squared error of from this function they created up here of the training set and the validation set. So this is on the training set and this is on the value set. And now we have a reduced number of leaves as well. Okay. This is just telling you other methods to do it. Oh, there's a paper on why you don't do this. Fascinating. I need to save this paper. Moving on to random forest. There's actually not just one random forest model. The one you'll find in scikit-learn is by Leo Brayman. It's his model, and there's multiple implementations of it, and the scikit-learn one is the most common. And there's other people who came up with their own implementations of a random forest model. But I think he's pretty standard. at this time. And so, how does it work? Random subset of rows, train, save model, and basically get a bunch of predicted models and average that out. And this is called bagging. It's not called boosting. Boosting models are like XGBoost, CatBoost. They're different. Um, Actually, probably should finish that little book I was making on just this. Like, I guess not a book, it's like 3 pages on the difference between a bagging and a boosting models. Um, oh, excuse me. Yep, different models make different errors. Basically, you improve the error rate because it's running a bunch of different models on different random subsets of data and taking that average. And they're going to teach us how to create it using the standard random forest regressor from scikit-learn. Take all of the arguments, run it through here with all the samples and fit it. That's what they do. And if you run it through now, the error rate has changed. And it's better than the decision tree regressor. The higher number you train, the better. I think it's like over basically a ton. You're fine. We'll train faster, little impact on accuracy. And now I'm thinking, I think I forgot to tell the team to look at the loss function. But that doesn't matter right now. Square log none, and you can see kind of how it classifies if the random forest classifier or a different example. Square result. Okay, so now it's predicting for each individual tree, showing the impact of operation for each individual tree. Yeah. So this is 0.23. This was 0.23. So that covers a different time period, a bit of both. Out of bags, yeah. Okay. So why is it overfit? It's because it's on different time periods, right? So how can you kind of fix that? So, yeah. So let's say you were training a model and that row was not included in training. That row can now be used as a separate validation set. And that is really useful when you have a small amount of training data. And it doesn't, so that you don't have to remove for the validation set. It's really useful for small data. And now for this particular type of training, because it's not always true when you're setting it up, you have to set it to true, it is lower than the validation. So in addition to, since it's lower, right, the error in the validation set might be from something else in addition to the normal generalization error. So how can we find out why this is lower than the validation set and what other error might be causing? Questions you might ask, and looking at tree variance. High standard deviations, yeah. Means they're very unconfident if the deviations of that row is high, right? So if we get the standard predictions deviation of the first 5 predictions, these are the deviations between the first 5 predictions, and they fluctuate a lot. For some auctions, there is a low standard deviation because the trees agree, and for others, it's higher. So this is a lower standard deviation. This is definitely a much higher standard deviation because it's not quite sure. And low confidence prediction will make you look twice. It's not normally enough just to know that a model can make accurate predictions. We also want to know how to make predictions. How it's making predictions. Can't read today either. So feature importance tells you that. And so mapping your feature importance is going to kind of tell you which one is being the most weight. And so these are the ones with the most weight. They should not be ones that are similar. And this is how they plot it out on a plot. Oh, important variables. Yeah, so removing anything that's less important than that makes sense. I've done this a few times to clean up data. Like, you don't need all the columns. Why are you training your data on all the columns when it's not even considering it for the model? Just remove it, which decreases your computation time and the runtime of your model. It's just bad code to have it in there. Bad practices. Subset of columns. So you can retain the model using the subset of columns. So we're using it with only the feature importance columns is what they're doing here. And now the training set and the validation set, still the same, but fewer columns to look at, right? Look at that. So that wasn't it. Redundant features, yes, 100%. So the columns that it thinks are pretty much the same. Machine ID and model ID. Drive system and secondary descent. Like, sometimes I've seen data where it really is the exact same column, and they like put the raw and the cleaned version, or like there's like this thing that wasn't, it was just, data quality matters. And in a lot of larger, older companies have a lot of issues with their data modeling because, well, they had to spring up these systems really quickly in a time where we didn't have standards of practice. And now that we know better, a lot of the newer companies aren't making these mistakes. But a lot of the bigger companies where most people will be working at, either as consultants or techs, you'll see a lot of it. Duplicate stuff, not just this. These are clearly two different pieces of information, and they're correlated, but actual duplicate pieces of columns. You'll see it in older stuff. So things that are merged early, product group and product descent are the same, so you can just remove those pairs as well. So here, if we remove these closely related features to see if the model can be simplified. Well, for one, calculate the rank correlation to see which one ranks higher than the other potentially. And then two, um, to remove closely related features will simplify the model without accuracy. So again, you're decreasing the number of columns that needs to run so that you decrease your computational speed and the time it takes to run your model. And so um, so they're running it again with get the OOP score, and then they remove their redundant values and get the OOP score for this. Dropping multiple variables. Still not any worse, but it reduces the size and they save it. They check it's not any worse, but it does save. So now what are we going to look at? Is understand the relationship between these variables and what it might mean, since there seems to be partial dependence between product size and year made. And what do they mean by that? The two biggest ones here, right? So they're looking at how many of each of the categories in product size, mostly null, some are not null. Year made, nulls, mostly not nulls. Yeah, so many things vary as the business grows. So you can't really replace. Um, so we're going to build partial dependency plots. And partial dependency plots try to answer the question, if a row varied on nothing other than the feature in question, how would it impact the dependent variable? How does year made impact the sales price, all other things being equal? And to answer that, we can't just take the average sales price for every year made. The problem with that approach is that many other things vary from year to year as well, such as which products were sold, how many were sold, how many have the air conditioning, inflation, and so forth. So merely averaging over the auctions for the same year made will capture an effect from other stuff that we don't want to capture, right? So instead, they replace every single value year made with 1950, since that is the null, and then calculate the predicted sales price for every auction and take an average of those auctions. And then we do the same for every single year until 2011. So they can isolate the effect of the impact of year made. Great approach. First, I don't want to hypothetically think through it. So with these averages, we can then plot each of the years on the x-axis and each of the predictions on the y-axis and find the partial dependency plot. So here, they plot all of the years, and here they plot the product size, right? Now, looking first of all at year made plot, and specifically at the section covering the years after 1990, which would be here. We can see clear, nearly linear relationship between year and price. Right. So it goes up, price increase as the years went on. Remember that our dependent variable is after taking the logarithm. So it means that in practice, there is an exponential increase in price as the years go on. This is what we expect. Depreciation is generally recognized as being a multiplicative factor over time. So for a given sales date, varying year made ought to show an exponential relationship to sale price. Now, this is weird. Very weird indeed, actually. It shows that this final group, which we saw for missing values, is the lowest price. To use this insight in practice, we want to find out why it's missing so often, right? Because this is the lowest price. Why are these prices missing so often? And what that means. So, missing values can sometimes be useful predictors. It is entirely depends on the cause of missing. However, they can indicate data leakage. So, data leakage. I didn't know about this paper. So, what do? And I don't want all the papers they've mentioned, but there's some I've been curious about, some concepts I've been curious about newer techniques for lately as I uh, manage more and more data teams. There's some things that I was told to do as an IC versus how I lead my teams to do as I'm in managing the workflow, right? That I need to kind of understand. And so, and actually wanted more of an architecture of management. But there's neither here nor there. Okay, so data leakage is subtle and can take many forms. In particular, missing values often represent data leakage. For instance, Jeremy competed in a competition designed to predict which researchers would end up receiving research grants. The information was provided by the university and included thousands of examples of research projects, along with information about the researchers involved and the data on whether or not each grant was eventually accepted. The university hoped to be able to use models to develop its competition to rank what grant applications were most likely to succeed so it could prioritize processing. Jeremy used a random forest model the data, and then the feature input used to find out which speakers are most predictive. He noticed three surprising things. The model was able to correctly predict who would receive grants over 95% of the time. Apparently, meaningless identifier columns were the most important factors. The day of the week, the day of the year were highly predictive. For instance, the vast majority of grant applications dated on a Sunday were accepted, and many accepted grant applications were dated on January 1st. Oh, wild. For the indicator columns, one partial dependence plot per column showed that when the information was missing in the application was almost always rejected. It turned out that in practice, the university only filled out much of this information after a grant application was accepted. Often, for applications that were not accepted, it was just left blank. Therefore, this information was not something that actually available at the time that the application was received, and it would not be available for predictive model. It was data leakage. Oh, that is wild. In the same way, the final processing of a successful application was often done automatically as a batch at the end of the week or end of the year. It was the final processing date which ended up in the data. So again, this information, while predictive, was not actually available at the time that the application was received. This example showcases the most practical, simple approaches to identify data leakage, which are to build a model and then check whether the action of the model is too good to be true. Look at the important predictors that don't make sense in practice. Look for partial dependency plot results that don't make sense in practice. Yep. I'm sorry. I didn't remember that. Uh, that's funny. And you can bet that happens more often than you think. Um, so, tree interpreter, we want to answer these questions, right? And they're stored in tree interpreter waterfall plots, charts. Okay, this is just the code to get set up. So prediction bias contributions. We get a waterfall. And it shows how the positive and negative contributions from all independent variables sum up to create the final prediction, which is the right-hand column labeled net. So how do these sum up to do these? So negative, positive, 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 negative, negative, positive. That's fun. Most useful in production rather than during model development. You can use it to provide useful information to your data product about underlying reasons as to why the predictions are doing stuff. Now, extrapolation neural networks. Yeah, they don't generalize well on new data. Extrapolation. So they are going to teach us about the extrapolation problem. And so we're going to create a random seed and create 40 random data points. They're going to change the shape of that and introduces an additional unit axis at that location. And now they'll create a random forest for that so that it's slightly different and provide it with new information. And then look what it did. That's not fantastic. So outside the domain that our training data covered. So we no cover this. It covered that. So the predictions were systematically too low. So what do we do when that happens? When it's out of the domain of what the model we trained on knows? Right. So they try to predict whether a row is in the validation or training set. So if you combine them together and you create a dependent measure that represents which data set it comes from, you can build a random forest using that data and get its feature importance. So here is the data that shows the columns we were looking at. And based on grouping them together and having it predict which set it was in, these are the ones that vary wildly, right? So sales time elapsed is very wildly different. Sales ID, machine ID. So it's basically how long it's been a long time. So if you remove these columns so that it doesn't, so it generalizes better, right? So if sales ID, hold on. So 23 to 8. It gets better if you remove sales ID. It gets better if you remove machine ID. It gets worse if we remove sales elapsed. So we can remove those two. And there we go. They removed it and it got better. Now it's more resilient to the changes of time that happens with the machine and the sales IDs. So it can uncover the domain drift. And there we go. All right, put it out. We recommend that often you should try building a model where your dependent variable is valid, like we did here. Yeah. So you're predicting if it's valid, and it can often uncover the subtle domain drift. Now, one thing that can help is to avoid using old data. Often old data shows relations that aren't valid anymore. So the most recent few years. Yeah. Okay. Yeah. Obvious. You don't necessarily need to train on all of this data. You might just need to train on a subset, right? And it improved even more on the validation set. Now, if we were using a neural network, what might that look like? So they do the pre-processing again, and this time they're removing the unwanted columns in a different way. And since it handles unwanted columns differently, they have to set it up differently. And so this is the way it works. They use embeddings. So to create embeddings, it needs to determine which columns should be treated as categoricals, and it does it by comparing the number of distinct levels in the variable of the max card parameter. So if it's lower, FastShare will treat the variable as categorical. Embedding sizes larger than 10,000 should generally only be used after you've tested whether there is a better way to group variables. So they'll use 9,000. Okay. Right. Categorical and abstract and a range of values. Let's verify concat split did the right thing. So it looks at the cardinality of all of the categorical variables. There are two variables pertaining to the model of the equipment, both very similar, very high cardinality suggests that they may contain similar redundant data. That would be this and that one. Note that would not necessarily see this when analyzing redundant features, since this relies on similar variables being sorted in the same. Oh, and these are the same too. Redundant. Got it. 666 is redundant 3, and there's number 3. So if I have a column with 5,000 levels, means there needs to be 5,000 columns in our embedding matrix, and we don't want to do that. So yeah, you want to remove model descriptor. Yeah, they removed it because there's so many embeddings. The other ones don't matter. They're small enough to not matter. Okay. So now they create a tabular pandas object. And it doesn't need to be normalized because it's a random forest. That's why I like it too. They do all of the stuff they normally would. Oh, we're in a neural network. So why are they normalizing? We're in a neural network, so it needs the normalization. It needs to make sure all the tensors are the same, so it does care more for a neural network than it would for a random forest. So they're going to use larger batch sizes. They're going to train this mug. They're going to get out Y min and Y max range for the regression model. They're going to create a learner for it, and they're going to set the loss to mean squared error. And this is what we got. They're going to fit one cycle. So, they were testing learning rates, min and max learning rates. And so they're going to just test one cycle. And this is what we got. Training loss here, validation loss here, and check where this went. And save it. This is a sidebar. I'm going to skip the sidebar for now. So now they're going to use a random forest and a neural network on top of each other to make a different ensemble model. And they give two different outputs, right? So PyTorch gives tensors out, um, and NumPy gives an array out. So here, they're going to convert the tensor to NumPy and feed it in to see if it gets a higher accuracy. So then we talk about boosting, which are your boosting trees, gradient boosting machines, gradient boosting decision trees. Very, very popular. And if you combine the embeddings with other methods, these are the other methods. So neural networks, random forests, boosting trees, neural nets, map, mean, average, percent error. So if you use using embeddings over raw categories, this is categories, all of them improve. They overfit. All right, and that gets us to the end of this one. All right, so it is 7:13, and that means um, NLP with recurrent neural networks. I don't think we'll have time to get through all of this today. Let me think about 15, maybe 30 minutes. What would we get through? If I want to stop there. Well, that's just white space. I think we'll just keep all the language stuff till tomorrow. I think we've covered most of this, most of what it really wants to cover, but it's teaching you more about how to use their specific stuff. So we'll save it for tomorrow. All right. As always, if you have questions, please feel free to DM me while we're doing this challenge. And go subscribe to the newsletter if you haven't already. Um, And yeah, I will see you guys tomorrow.